Good morning, students. This is the third part of today's lecture. In this lecture, we will talk about more about advanced attention models, and especially we will introduce the transformer model. Now, we have earlier talked about attention networks, and we have seen that attention shows that when we want to do a particular task or a particular state, it shows which position in the input attention is focused on. So attention can be used to understand the output, and attention can be seen as a mechanism of providing explanation. Deep networks in general are inscrutable. They do not model data using features like classical ML models, but attention maps are explanations of net behavior because they identify the influential parts of the input stream. Now, we have seen that recurrent networks, while they can be made powerful using attention, they have some inherent drawbacks. One of the major drawbacks is that in recurrent networks, training and inference is sequential. Because of the sequential nature of an RNN or LSTM, one cannot speed up the computation using parallelization. In contrast, in a convolutional neural network, the kernels can be applied to the different positions in parallel. RNNs, on the other hand, are hard to parallelize. Secondly, we have seen that long-range dependencies have to be remembered across many single time steps, which can be mitigated to some extent by using attention. Thirdly, it is tricky to learn hierarchical structures like car, blue car, into the blue car, etc. Now, some of these problems are addressed by convolutional networks, but convolutional networks have other limitations. They do not capture the complete sequential nature of the input. Now, we have discussed about attention in the first lecture today. The particular type of attention that we used is called encoder-decoder attention. In encoder-decoder attention, you find while you are in a state of the decoder, you find out which state of the encoder attention is focused on. So apart from encoder-decoder attention, this attention mechanism, because it is so powerful, it can be used as self-attention within a layer itself. For example, suppose you consider a sentence comprising of T words, W1, W2, W capital T. Now, you have an RNN or you have hidden nodes which capture representations of W1, W2, Wn. Now, you can have a multi-layer representation, a deep network with multiple hidden layers to capture the representation of the input. What if we use attention to capture this representation? So, we can think of self-attention as an attention mechanism that relate different positions of a single sequence. Suppose x5 is a particular word at position 5 and z5 is the representation. So we have x5 or xi, and suppose we have zi as the representation of xi at a particular layer. Now, this Zi, what if we use attention to compose Zi from the different other positions in the input sequence? And we can look at the entire input sequence from x1 to x capital T and let Zi get inputs from all of them via some attention weights. So self-attention allows information flow within the same set subnetwork. So we can have self-attention within the encoder or self-attention within the decoder. Now, then the major major thinking was that since attention-based networks are so powerful, what if we completely forego a RNN or even a CNN and go for an attention-only network? And there was a powerful paper in 2016 by Vaswani et al. The paper title is "Attention is All You Need." In this paper, they showed a network which does not have CNN or RNN but uses solely attention to get a good representation, and it was shown to be very powerful and useful for using as neural machine translation. Transformer-based methods have also been used for contextual word representation. So we will talk about transformer in this lecture, and the following slides have been designed based on a lot of material from this particular slide. So this particular site has information about illustrated transformer, and this has been followed in developing the current lecture slides. Now let us see what a self-attention is in a picture. So an attention mechanism, as we saw, relates different positions of a single sequence in order to capture a representation of the same sequence. What do we mean by this? Suppose this is the input sequence x1, x2, x3. x1 is the word je, x2 is suis, and x3 is étudiant. That is, I am student. Je suis étudiant. Now this is a self-attention layer, and via the self-attention layer we are finding the representation of x1, x2, x3 in the next layer as z1, z2, z3. Now z1 is obtained from the vector of x1, the vector of x2 and the vector of x3, or something that can be obtained from x1, x2 and x3. And so we compose these vectors via attention weights, and these attention scores are computed for this position in the first representation layer and the similarity of that or some function of that and the input in those positions. So Z1 can be obtained from X1, X2, X3 via some attention score. Similarly, Z2 can also be obtained from X1, X2, X3, and Z3 can also be obtained from X1, X2, X3. This is called self-attention. And you can have multiple layers of self-attention. So you could have the next layer W1, W2, W3 or V1, V2, V3, which can be obtained from W1, W2, W3 can be obtained from Z1, Z2, Z3. Now in the self-attention block used by Vaswani et al. In their paper, they defined an encoder block which comprises of one self-attention layer and one feed-forward network. So there is a feed-forward network which goes from Z1 to the output of this encoder, and the same feed-forward network is shared by the different positions. So this is one block in the encoder. A transformer can have multiple blocks in the encoder which are stacked one after another. Now let us see, let us look at how self-attention, how it compares with convolution. In the class you have previously looked at convolution layers. In convolution layers you have seen that the output at the next layer corresponding to one kernel function is obtained from the input layer in the positions which are neighboring this position. So if this is position I, you look at the neighbors in the, let us say, positions I minus 2, I minus 1, I plus 1, I plus 2. From these inputs via the kernel weights, you compute the representation for this kernel at the next layer. This is a convolution operator. In contrast, in self-attention, the value at this layer for a particular head or a particular attention head. An attention head is analogous to a CNN kernel. For a particular attention head, the representation in this layer is composed from the vectors, all the vectors in the input, all the input positions or all the positions in the previous layer. And how much they contribute to this position is via the attention weights. So the dark black lines are where we have higher attention, and the lighter lines is where you have less attention. So while in convolution the kernel size is finite, let's say 3 or 5, something like that, in self-attention you are looking at the entire input. So there is no restriction on the kernel size. What about the weights? In convolution for a particular kernel, the weights are learned and they're fixed. So if you have 10 kernels, for each kernel you will have these 5 weights, and these 5 weights are fixed. In self-attention, on the other hand, you compose this from all other inputs via an attention score. How is the attention score found? The attention score is found by using some similarity or some function of this node and this ith node and the nodes at the other positions. And this similarity function is a same function, is one function for each attention head. So you could use a function such as dot product, or you can use a neural network which takes the ith position and the jth position as input and is trained to learn the attention score. Now, if you look at attention in encoder-decoder networks, the Badanau model, then the Luong-Pham-Manning model, they discussed attention, which is called encoder-decoder attention. That is, you learn how to find for a particular decoder state which encoder state attention is focused on. On the other hand, one can talk about two other types of attention. One is encoder self-attention and the other is decoder self-attention. So within the same representation, within the same encoder, you can have multiple attention layers. So for this position, attention is obtained from these three positions. Similarly, from here, attention is obtained from this, and this position, attention is obtained from all these positions. On the decoder side, also we can use self-attention. However, we have to do it carefully depending on the model. Suppose you are using this model, encoder-decoder model, for machine translation, and you generate words one after the other from the left to the right. So when you consider attention for the second position, the third position word is not yet known. So attention has to be restricted only to those words which have already been generated. So if in this case the attention is restricted to the values which have been generated so far, this can be achieved by masking the remaining positions. So you take into account the values of those positions which have been generated and you mask the other positions, and then self-attention can also be used. Now, if you use this sort of attention mechanism, it is possible that you do not use a recurrent network at all and only use this attention mechanism. Now, let us look into more detail about transformers. As I have told, this transformer came from this paper. This paper came in archive in 2017. The title of the paper is Attention is All You Need. It is by Vaswani et al. So in this paper, they gave the architecture of this neural network model called transformers, which uses attention and only attention and no convolution or recurrent steps. So self-attention mechanism models relationship between all the words in a sentence. For example, you consider this sentence: I arrived at the bank after crossing the river. Now, when you look at the word bank, and if you want to understand that the meaning of bank, uh, the meaning of the bank in this sentence depends on the word river, then in order to understand this representation of bank, you must give a lot of attention to the word river. This can be done by an attention model. So to compute the representation in the next layer for the word bank, the transformer will compare the word bank to all other words in the input sentence. And for each of those positions, there are 5, 6, 7, 8, 9. There are 9 words in this input sentence. For each of these positions, it will compute an attention score. And this attention score will determine how much of each of these words will contribute to the representation of this fifth word at the next layer. So this is a schematic diagram of an attention mechanism. These are the different words or input at time t minus 1, t and t plus 1. And after the self-attention, we generate the representation at the next higher layer. Now, instead of only using the word, this transformer produces a generic mechanism where from this word, we get 3 different representations: query, key and value. Query is used for the query representation of the word as the query. For example, if I am looking at the representation in the fifth position, then this is my, the input at this, the value at this position is my query. And from a particular word, we can either use the word itself as the query, or from the word, by projecting it onto a vector, we can get the query vector corresponding to the word. Similarly, we can look at the key corresponding to a word. The key of a word is when you compare this word, the query, with a word in another position, you use the key of the word to do the comparison. So comparison of similarity or attention score is obtained by looking at the similarity of the query of this word to the key of the word in this position. So it is not just the word. In the first 0th level input, we have the word, and subsequently as we go up the stack, we have a representation. So the query of this representation is compared with the key of the representation in the jth position. And based on that, an attention score is computed. Let's say score I is computed. And when we get all the attention scores for all positions in the sentence, we can use Softmax and we can get the attention values alpha I corresponding to these positions. Now, once we get this attention, these alpha I values, then with alpha I, we compose the values corresponding to these positions. So the key vector, the value vector and the query vector can be obtained from this vector representing the word or a representation of the word at a particular layer. Now, let us see how a transformer looks like. In transformer, we have an input. Suppose this is a German sentence, komm bitte her. This is the input. And then we can have a number of encoders, stacked encoders, which processes the input at different layers. So 1, 2, 3, 4, like that. Suppose we have 8 encoders. And then the output of the final encoder stage is fed to the decoders at all the layers. So as we saw in a transformer, each encoder comprises of one self-attention layer and one feed-forward layer. And we can stack multiple encoders. The encoder at the last layer gives input to the decoders at different layers. And the last decoder layer gives the final output. Let us say in this case, the final output is an English sentence, please come here. So the transformer, how it works, it starts by generating, given these actual 3 words, come bitte her, it starts by generating initial representation for each word. You can use word2vec or there are other representations possible like fast text, glove, etc. So these representations are used. Then self-attention is used to aggregate the information from all the other words. For each position, you aggregate information from all the other words to generate a new representation of the word at first self-representation, self-attention layer. Now this encoder is, after we get out of the encoder, we get Z1, Z2, Z3 or Z11, Z12, Z13. Then again there is another encoder. We get the representation at the next state, Z21, Z22, Z23 from Z11, Z12, Z13. And this can be repeated multiple times for all words, and these operations can be done in parallel, because for each word, when we are finding the attention with the other words, when we are doing it for word at position 1, we can simultaneously do for word at position 2 or 3 or 4 or 5. So these operations are parallelizable, and at each layer we get a new representation at higher levels of abstraction. Now, how attention works in a transformer? We are showing a simplified transformer having only one encoder and one decoder layer. But as we said, we can have multiple encoder layers. The last layer of the encoder will feed to the decoder, all the decoder layers. So the encoder's input first flows through a self-attention layer. The outputs are fed to a feed-forward network. The exact same feed-forward network is independently applied to each position. Now, the output of this encoder, final layer encoder, goes to the decoder. Decoder has the self-attention and feed-forward layer. In addition, the decoder has an encoder-decoder attention layer. We've already talked about encoder-decoder attention when we talked about Badanow's model in the first part of today's class. So decoder has a self-attention layer, and it may be masked self-attention. Then there's an encoder-decoder attention, and then there is a feed-forward layer. Now, in the encoder, just to elaborate it more, suppose you have this word thinking and the second word is machines. The word thinking, we have the encoding of the word thinking in a word vector. Then we have this self-attention layer through which we compute Z1 by taking attention from all these positions, and then we compute Z2. Then there is a feed-forward network. The same network is applied on Z1 and also applied on Z2. From Z1 we get the R1 and Z2 we get R2 as the representation of the next layer. So, I'm illustrating this again with the following sentence. So this is the sentence which is input. The animal didn't apostrophe T cross the street because it was too tired. Suppose we are considering the word in the position it, and we want to find the representation of it. So we can compute attention for each position in this sentence, and maybe this attention is higher for the words the animal or T and lower for other positions. And based on the values of these words or these inputs and the attention weights, the representation of it in the next layer is computed. Now let's look at the detailed steps involved. The first step is to create the vectors. So we take the words, and for each word we create 3 vectors: query vector, key vector and value vector. Sometimes these vectors, like for example in many NLP applications, the value vector is taken as the word itself. But query vector could be taken as the word itself, or key vector could be taken as the word itself. But in the general case, from the word you can obtain the query, key or value via some parameters. So we learn parameters WQ, WK and WV, so that by taking a product of the query vector and of the word and WQ, we get the query vector. From the word and WK, we get the key vector of a word. The word and WV, we get the value vector. So for the word thinking, uh, which is whose embedding is x1, machines whose embedding is x2. From x1 and WQ, we have got Q1, x1 and WK, K1, and so on. Similarly, we get Q2, K2, V2. Now we come to step 2. In step 2, we will calculate the scores. Suppose we are calculating self-attention for the first word thinking. So we want to find the score of thinking with the words in the position 1 and position 2. If there were 3 other words, so we will find at positions 1, 2, 3, 4, 5. Now the score that we compute is we find the similarity of, so we take the query of thinking. So that is Q1. So because this is my query position. And when we are looking at the score for the same position, you take Q1.K1. If you are using dot product as the similarity, we take Q1.K1 as the score of position 1. And we take Q1.K2 as the score of position 2. In general, for the ith position, we take Q1.Ki, and we will get the scores for these positions 1 to I up to capital T. Then in the steps 3 and 4, in step 3, we do some sort of scaling. Because we are taking the dot product score, dot product may become very large. So we scale it down. In this case, in the transformer paper, they used the key vector had dimension 64. And the size of the key vector impacts how big this dot product becomes. And they suggest that we scale by the square root of the size of the key vector. In this case, square root of 64 is 8. So we divide the score that we obtain by 8. And after that, we get the scaled down version. So initially we get 112 and 96. After scaling, we get 14 and 12. And then we do softmax here because there are only 2 words. After getting softmax, we'll get the probability values as 0.88 and 0.12. So 0.88 is the attention weight at position 1 and 0.12 is the attention weight at position 2. Now in the step 5, we multiply each vector by this softmax score. So when we consider the position 1, we consider V1 as the value of interest corresponding to position 1. So we multiply this score into this value V1. So 0.88 into V1 plus 0.12 is the attention score of position 2. We do 0.12 into V2 to get Z1. Similarly, we can, for the word machines at position 2, we can find the attention score at position 1, attention score at position 2, and then we can multiply the first attention score with V1 plus the second attention score with V2 to get the representation of Z2. So this illustrates the matrix calculation of self-attention. We have the word X and its word vector representation. We multiply it by WQ to get the query vector. We take, so the words, we can have multiple words, X1, X2, X3, etc. When we multiply them with WQ, we get Q1, Q2, Q3 for the different words. Similarly, we can multiply by WK vector to get the keys and WV vector to get the values. Now, so to summarize, the output of the self-attention layer is softmax over this Q into KT divided by root of DK. And with this, we multiply V to get Z. Now, this shows the process that we do for one attention head. In convolution, you have studied that you can use multiple convolution kernels. In this case also, we can use multiple attention heads to get this multi-headed beast called multi-head attention. So these attention heads and the computations for them, they can be done in parallel. Each head will use a different set of linear transformations. Just like in convolution, each kernel has a different set of parameters. For multi-head attention, the WB, WK and WQ vectors will be different for each head. And therefore, just like in convolution, we say we use multiple kernels so that they can learn different features. In this case also, we can see that we can use multiple heads and they are learning different types of relationships. Now, if we look at the schematic diagram of the transformer, we'll see that we have multiple set of query key value matrices. So for example, we use H number of heads. So for each head, we have the VKQ values. So we have V1, K1, Q1 for head 1, V2, K2, Q2 for head 2 and VH, KH, QH for the head H. So we have multiple sets of these QKV matrices. Now the transformer given in Vaswani's paper uses 8 attention heads. So there are 8 sets of encoder decoder and each of these sets is randomly initialized. After training, each set is used to project the input embeddings into a different representation space. So multi-head QKV gives this head 1, head 2, head H at the different heads and that is composed with WO. And each of the heads, head I, this is WO corresponds to the output bits. Head I is obtained by using attention on QWQ, KWK, VWV, all of them indexed by I. This is for the ith head. Similarly, you can have 8 different heads. Now, so with multi-headed attention, we maintain separate QKV weight matrices. So we'll have 8 different matrices for QK and V when we use 8 heads. And for each head, and these matrices will be different. So this picture illustrates 2 different heads. For each head, we have these matrices and we have the corresponding projections. Now, suppose we have these 8 outputs for a particular position. We need a way to condense these 8 down to a single matrix so that we can feed it into a feed-forward network. So we have the Z0, Z1, Z7 from these 8 heads, which calculate attention separately in 8 different attention heads. Now these 8 outputs, Z0 to Z7, can be concatenated. After concatenation, we multiply this with the weight matrix WO that was trained jointly with the model. And the result would be a Z matrix which captures information from all the attention heads. And we can send this forward to the feed-forward neural network. So to summarize, suppose we get this input sentence thinking machines. We find the embedding for each word thinking and machines. Then we have split into 8 heads. We multiply X or R with this weight matrices. X with these weight matrices. Calculate attention using the resultant QKV matrices. Concatenate the resulting Z matrices, multiply with the weight matrix WO to produce the output of the layer Z. So we can do for X, and after the first layer, suppose R is the next layer. On this also we can use the same process at all layers to get the output of that layer which goes to the next layer. Now, we told that in attention networks, we do not use recurrence or CNN. Since we do not use recurrence, we lose the information of how the words are following one another. So this ordering information is a very important information among words in natural language processing. So in order to offset this, we add some information to each input, which is called the positional encoding. Now these vectors follow a specific pattern that the model learns, which helps it determine the position of a word or the distance between different words in the sequence. So we have this input word je, x1 is its embedding, t1 is a positional encoding, and x1 and t1 are composed to come up with an embedding which incorporates this time signal. So similarly for x2 and x3, we apply these positional encoding and combine them to learn the new embedding for the words which captures the positional encoding. So by this positional encoding, by applying it to the network which uses only attention and no recurrence weights, it's possible to capture the sequentiality of the input. And the advantage is, while in RNN we cannot parallelize the process, this process is eminently parallelizable. So the order of the sequence is represented with this positional encoding. Now we look into the transformer block diagram. In transformer there is this input layer and the encoder layer and the decoder layer. Encoder we may have multiple stacked layers, and decoder also we can have multiple layers. Each of these, both the encoder and decoder stacks have attention. Like here we have self-attention. Then we have a feed-forward network at each position. And we also have positional encoding. So we have the word and the input embedding. With the input embedding, we combine positional embedding to get the new input encoding. Then we have a self-attention layer where we have multi-head attention. After the output of that, there is a normalization called add and norm, and this output feeds to a feed-forward network. In addition, there is skip connection from this, from here to here and from here to here. So skip connections, as you know, are shortcut connections which help in the deep network having close access to previous depth inputs. If you look at the decoder also, we have the output encoding, the positional encoding, masked multi-head attention, then add and norm layer. Then there is the encoder-decoder attention, which is again multi-head, then add and norm, then a feed-forward network, then again a normalization. And here also we have this skip connection. And finally, the output from the final decoder layer is a linear mapping to the softmax function. What is the role of this linear mapping? Suppose this output here for this word has 200 dimensions. The softmax, the size of that vector depends on the total number of words in the vocabulary. So we do a transformation to get from this vector to a vector of size capital V, where V is the number of words in the language. Now we saw the skip connections. They're also called residuals. So each sublayer in each encoder has a residual connection around it and is followed by this normalization step. So we are showing this in greater detail in this picture. You have the word thinking and its encoding, then positional encoding, then a self-attention layer. There's a residual connection from this layer directly to the add and normalize layer. This also feeds to the add and normalize layer. The output goes to the feed-forward network, again an add and norm layer, and this is another residual connection. So, so this is showing more details. The input after self-attention from xi we get zi. Then this normalization is done. So we get next version of zi put to a feed-forward network where we get a Ri. And this same feed-forward network is shared between position 1 and position 2 and all other positions. And therefore, a transformer model can work on sequences of arbitrary length. Now, when we have a stacked encoder, we are showing a two-layer stacked encoder. This is encoder 1, then this is encoder 2. Encoder 1 gives output to encoder 2. Output of the last encoder layer is fed to the decoders. So we have, suppose, two decoder layers. This is decoder 1, this is decoder 2. The same output is fed to both. And each decoder layer, there's a self-attention and a norm. Then an encoder-decoder attention add a norm. Then the feed-forward network add a norm. This is one unit of the decoder. We can have multiple units which are stacked. It shows decoder 2 without the details. And finally, we have a linear network which converts it to softmax. So, if we look at the decoder side, the encoder processes the input sequence. The output of the top encoder is transformed into a set of attention vectors k and v, and these are used by the decoder in its encoder-decoder attention layer. So decoder has two attention, the self-attention, which looks at the previous words which are output, and the encoder-decoder attention, which takes input from the encoder side. So this is an animation showing how it works. You have the input feeds to the first encoder layer, then the second encoder layer. So the input feeds to the first encoder layer, the second encoder layer, then we have the Q, K and V vectors, which we have this K and V matrices from which we get the output to the decoder. And then we have these two decoder layers, and finally we have this linear and softmax layer from which we get the output. Okay. So another animation here, the input is this words, Jersui etudio. The embeddings are computed, embedding with time signal goes to the encoders. This is the output which goes through this, projected through these matrices to the decoder. And after the first output, the previous outputs are used in the self-attention layer, and we have the encoder-decoder attention layer which goes to the linear and softmax unit and produces the remaining words in the sentence. Okay, so this was shown by this animation. And finally we get the end of the sentence. So let me run this animation once more for you. So after the first word, we are taking that as input, generating the second word, then the second word is taken as input, and the third word is generated, and so on in the decoder side. I am a student, then we get the next word. The student is fed here, it's embedding, then it gets attention from the encoder decoder, then end of sentence. So in the decoder, the self-attention layer is only allowed to attend to earlier positions in the output sentence. This is done by masking the future positions before the softmax step in the self-attention calculation. The encoder-decoder attention layer works like a multi-headed self-attention, except it creates its queries matrix from the layer below it and takes the key and value matrix from the output of the encoder stack. Finally, there's a linear layer and a softmax layer. There's a softmax layer to the output word. The linear layer is a fully connected neural network that projects the vector produced by the stack of decoders into the logits vector, whose size is the size of the vocabulary. Suppose your vocabulary size is 10,000, then this logits vector will have 10,000 as its size, and each cell corresponds to the score of a unique word. The softmax layer turns these scores into probabilities so that all of them add up to 1. The cell with the highest probability may be chosen as the output, and the word associated with it is produced at the output of this time step. So, and then, if we find that the position 5 we have the highest probability, we will output the word corresponding to position 5. So you may refer to these two slides to understand about transformers. This second link is what I used to make these slides. There's another blog, Google ai.googleblog.com, 2017 August, Transformer Novel Neural Network. You might follow it if you want to get an understanding of this, or this blog, jalamar.github.io. And most importantly, you should look at the Vaswani's paper, Attention is All You Need. If you read this paper, you'll get a good idea about the transformer networks. Now, transformer networks have become very useful, and they have obtained the state of the art in neural machine translation. Not only that, transformers have been used to come up with a representation of the words in the sentence from multiple layers. And this is done so that, BERT is a word representation by Google, which uses a transformer of, let's say 12 depth. Each depth we have a transformer, and in this transformer, by using self-attention, you compute the different feature function values at different layers. And finally, when you give the output of the word, you don't not only give the output of the word as the 12th layer, the output representation, but also you make available these feature functions, which can be used as representing the context of this word. And the use of such embeddings like BERT and all have pushed the state of the art in most NLP applications. Finally, we talked about attention and interpretability. As I mentioned, attention methods learn to predict the positions of the input which are important or salient positions. And attention visualizations help users understand the cause of the network's behavior. Not every attended region may be actually important, but we can use post-processing to remove it, and we can use the output, we can use the attention weights to understand and interpret how this network works. So I will stop today. If you have questions, please email them to me and we will arrange a way of discussing them. Thank you very much.